the beginning of the last unit, we are going to start looking at the law of sines and the law of cosines, which if you've looked on Canvas, you know what we're really focusing on is solving these oblique triangles or non-right triangles. Most of the trigonometry that we've dealt with is right angle or right triangle trigonometry, or kind of extensions of that. We put things on the unit circle so we can think about different quadrants, but we're still really focusing on those right triangles. So based on the definition of our function, sine, cosine, tangent, cosecant, secant, cotangent, all that stuff, we have, at their core, they're really based on side lengths of these right triangles. So we're going to derive the law of sines, which is going to help us to solve oblique triangles. And then we've got this weird ambiguous case that we'll have to look at, which I think is kind of interesting. So that's what we're up for today. So the law of sines is really simply put, it says the ratio of the sine of an angle and the angle's opposite side is just constant. It's the same. So the ratio of the sine of capital A and the length of side length A is the same as the ratio of angle B's sine output with the side length of B. And then we could do the same thing for C. What we're going to do to derive this or prove it or whatever is we're going to focus on connecting angle A and B here with their side lengths, showing that that ratio is consistent across those two angles. And if we can do that, then we'll be able to just say, well, what if we just switch things around and then made one of them C instead? So really, if we can show that it's the same for two, then we're really going to show it's the same for all three. So this is what we've got so far. I'm going to erase some stuff. Let's get rid of those. I've drawn, or I've put on this triangle, a nice vertical line dropping down from angle C to get this nice right angle here. So we're cutting this up into two right triangles. And then we can just look at the sine of each of our angles, A and B. And since we have right triangles here, we've got this nice one here for our A angle, and we've got this nice one here for our B angle. Since we have those right triangles, we can define our sine outputs. So we've got that sine of A is the opposite side, H, over the hypotenuse, B, and sine of B is the opposite side, H, over the hypotenuse, A. And notice that we can solve both of these for H, and we get little b sine A by just multiplying both sides of this, moving that b up. And then we can do the same thing here. Notice, though, that h in both cases are really the same thing. This length is the same for both triangles. So really, these two things are equal to each other. So that's what we'll do. We'll say, hey, we can set these things equal to each other. And then since we want to talk about a ratio, we'll divide some stuff. And so we've got side length A over sine of angle A is the same as side length B over sine of angle B. And so how could we do this for the other one? Well, if you wanted, what we would do instead is we would cut up this into a nice right angle, and then we'd label this H, and we'd say, all right, we've got a right triangle here, there's our right angle, and then there's another one here, and we could connect the sine of A and the sine of C, and so then all three of them will be the same. So this is the law of sines. If A, B, and C are the measures of the angles of some triangle, notice it does not have to be a right triangle. It can be any triangle. Then lowercase a, b, and c are the side lengths. Then we've got these two statements. Notice that these are just reciprocals of each other. Since we're talking about consistent ratios, it doesn't really matter which version is on top and which version is on the bottom. So we'll just pick whatever's convenient mostly when we're actually trying to solve some stuff. So let's just take a look at some examples. So here's an example where we have some angles. We've got one side length. Notice right off the bat that we actually are given three angles in this case. If you're given two angles, you know the third. How come you know the third? Well, this one here is just going to be 180 degrees minus 78 degrees minus 32 degrees. So since all the angles in a triangle have to add up to 180, these two add up to 110 10. Is that right? Yep. So then this angle is 70 degrees. So this is really like if we had all three angles. Now we have a side length. We've got these two connected to each other. This is our side length C and our angle C. And so what we can do now is we can go ahead and say, I'm going to move all this. I'm going to put my 70 degrees on the inside, so it's giving me some more room to write. So we could set up that ratio of the sine of 78 and the side length of 6. So this was 70 degrees. So what we can say is sine of 78 degrees over 6 is equal to sine of 70 degrees over lowercase b, where that's right there, and that's also equal to sine of 32 degrees over lowercase a, and lowercase a is right here. So notice if you just take one of these, or like a pair, I mean, you can solve this for b pretty easily. So what we've got is that b is equal to, it might be easier actually to write this as 6 over sine of 78 degrees equals b over sine of 70 degrees, because now you can just multiply sine of 70 degrees on both sides. So we'll say this is 6 sine 70 over sine 78. And if you have a calculator, make sure that it's in degree mode. I actually have one this time. 6 sine 70, and I'm in degrees, divided by sine of 78. I've got that this side length is right around 5.76. So that's what this side length here is, 5.76. Then we could do the same thing for A, and we could say A is going to be the exact same thing as this, except instead of sine 70, it's going to be sine of 32 degrees. So we've got 6 sine 32 degrees over sine of 78 degrees. And we can plug that into our calculator again. 6 times sine of 32 degrees divided by sine of 78 degrees. And I've got 3.25-ish. So normally what I'll do on assignments and things like that, just to make it all pretty clear, is I'll actually give you somewhere a list of little blanks that you can fill in. So since we're looking for angle B, I might give you something like this. And then since we're looking for side length B and side length A, I might do something like this. Let me put some space in between there so it's easier for me to write. That way, you can do all your work, and then just really quickly and easily and succinctly, you could say, all right, angle B, we said, was 70 degrees. Side length B, we said, was 5.76, and then side length A was 3.25. Cool. So that's what we've got. Here's another example. It's pretty much the same kind of setup. 2 angles, a side length, and we will see what we can do. Notice you can find that third angle right here. I'll do that with you, and then I'm going to leave you some space to see if you can fill in the rest. So our third angle, what are we at right now? 79 degrees, and we need to add up to 180, so this is 101 degrees. So now you've got this connection right here that you can use to find your other 2 side lengths, and I will give you some space to do that. So pause the video, see if you can fill out the rest of these side lengths of this triangle, lowercase b, lowercase a. Go. All right. Hopefully you went ahead and did this. If not, don't look at this. Go back and do it yourself. All right, here we go. Let me just kind of run through this real quick. So I'm looking at this connection here. So I put 4 over sine of 101 degrees, and I'm going to connect that with these 2 side lengths, which maybe I'll draw in blue. Or not 2 side lengths, this little angle and side length. So side length B over sine 41 degrees is equal to side length 4 over sine of 101 degrees. And then we can solve for B pretty easily by just multiplying. And 2.67 is what we get. We can do the exact same thing for A here. Notice that I still compared this with the angle C and side length C, because those two aren't rounded. I always try and use the exact values. I know that this angle is exactly 101 degrees because I know that everything has to add up to exactly 180 degrees. This side length I know is approximately 2.67. It's actually 2.67 blah 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 blah. There's some other stuff there. So if I use this value here, then what you're going to do is you're going to get something that's even just a little bit more slightly off because you're using a rounded value. This is a little bit wrong, and so then when you round things at the end, it's going to be actually a little bit worse. So try and use whatever exact known values you have, and you can. That typically works out pretty well. All right, so hopefully these examples aren't too bad. The thing for you to notice, I think, is that we're given, in this case, 2 angles, which really means we're given 3 angles and a side length. So as long as you have 2 angles and a side length, this ends up being pretty easy. In this case, we call this ASA because we have an angle and a side length in between them and then another angle. If we go back to the last example, we had an angle and then a side length that wasn't in between, so we call this one like AAS or maybe SAA, side length, angle, or if you read it the other way, angle, side length. Notice that it's the same thing. ASA and AAS and SAA are all the same thing. As long as you know 2 angles, maybe I'll type this here. If you know 2 angles, you really know 3. So this setup really just corresponds with knowing all the angles and a side length. You have to have a side length here because we have to be able to set up that consistent ratio that we can kind of connect to all the other ones. So the question is, what if we don't know 2 angles? Then we don't know all 3, and so we have these other 2 cases. What about a triangle that looks like this? That almost looks right, but let's pretend that that's not. And let's say that we know this side length, this angle, and this side length, SAS. Or what if we have a triangle that looks like this, and instead we know a side length, and an angle, SSA. So what happens if we only know one of the angles? Maybe it's between side lengths, maybe it's not. Notice that in this one here, we have a connection. We have an angle and a side length that's opposite it. We can use the law of sines. For this one, this SSA, this red one here, I'll just type this. We don't have an angle and opposite side length. We can't use the law of sines. I don't know why I'm in a typing mood today, but that's what we've got. So because there's no side length opposite this angle, or there's no angles opposite these side lengths, and we can't find them very easily because we don't know what both of these are. We know that all of them have to add up to 180, but now there's 2 of them that are unknown. For this version, we can't use the law of sines. For this, though, we can. But this is going to be a bit more interesting because there's some cases, some options, some things like that we can have. So if you remember at the beginning of the video when I said we're going to look at the ambiguous case, this is what we're going to look at because there's some things that happen here. So the ambiguous case is this really interesting specific thing, but I want to show you there's really 3 different cases that we have. So here's our first 2 cases. If we know an angle and a side length, and we call it SSA instead of ASS for obvious reasons, then maybe everything is just pretty normal. We get a triangle. It works out the way that we think it does. Every now and then you might end up with a right angle triangle. That could happen, but who cares? But everything just works out really nicely. But it's possible that if you only know this angle, this side length, and this side length, maybe this side is too short. And so no matter how you swing it, let me kind of show you what I mean by swing it. No matter what this angle is, if you swing this back and forth, it never actually connects to this base of our triangle, because maybe this side length is too short, or if you want to think about it a different way, we could say the angle that we know happens to be too big. If this angle is a really, really large angle, and this is a short side length, then it's possible that it doesn't reach down far enough. A really kind of obvious thing is that big angles correspond with big opposite side lengths, and they go in the order that you'd think. The biggest angle has the longest opposite side length. The next biggest angle has the next longest side length. And so you can kind of notice that right off the bat. This B side length is really long, and this A side length is really short. If this is a big angle, then this is supposed to have a nice long side length. So it's possible that that's too short. We'll have to investigate how that'll look. But really what it's going to end up with is you're going to be looking at some sort of a sine of an angle, and it'll end up being bigger than 1. And you'll say, wait a second. Sine only outputs things in between -1 and 1. This can't happen. And so you'll end up noticing some stuff like this. Then we have this. This is the ambiguous case. It's called the ambiguous case because we have multiple solutions here, and we're not sure which one. Now, sometimes people will call just SSA the ambiguous case. Sometimes people will call this specific setup the ambiguous case. So depending on where you read this, you might see the ambiguous case referred to as just this setup, or this possibility where you have a side length, but it can swing around and touch the base at a different angle. There are two options for that consistent length here. So this is a really interesting one. The reason that this is going to happen is because we're going to end up with some sort of like a sine of an angle here. And it's going to equal some number. And you're going to want to figure out what is that angle. And if you do that, you could use an inverse sine. But we know that inverse sine only gives us one of the possibilities. And so what we'll really think of is that if you've got some value, it could be here or here, and we have to think about which angles make sense, and sometimes both of them do. So in all of these cases, you're going to have to think about that. Now, in some cases, you're just going to have like sine of an angle is equal to 2. And so you'll say, well, it doesn't matter what the angle is. That's never going to happen. Over here, you might have sine of an angle equals some number, and you'll do the inverse sine thing, and you'll figure out that only one of the angles makes sense. You've got two possibilities here, but maybe one of them is too big. And so if you know an angle already is 50 degrees and you find that the other possibility is 140 degrees, well, that doesn't make sense because that adds up to 190 degrees. That's more than what we know is in a triangle. You see what I'm saying here? So when we look at these two possibilities, sometimes both will actually be possibilities. We'll get two separate triangles. We'll get this big one here with a larger angle, or we'll get this small one here with a smaller angle. And so we'll just have to kind of consider that. So this is a weird case in the law of sines. Let's take a look. No pictures, nothing like that, because we don't know what this triangle looks like, because it could look like any of these three cases here. So anyways, notice we have a pair of angle and side length, and then we've got another side length here. So this is our SSA or something like that. So I'll say this actually is the SSA because we've got one pair of opposite side lengths and angles. Excuse me. So what we can do is say sine of B, maybe I'll leave off the degree, over 7 equals sine of 52 degrees over 10. And so we can say sine of B is 7 sine of 52 degrees over 10. So if you want, you can figure out approximately what this is. Let me grab my calculator. 7 times sine of 52 divided by 10. I've got that as right around 0.551, but instead of writing that down, well, I'll write it down here, 0.551. I'm going to use my sine inverse of all this stuff, and I'm going to use the exact value instead of the rounded version. And so B is going to be approximately 33.5 degrees. But we have to be careful here, because remember that 33.5 degrees is right here. This angle could also be this one, which is 180 minus 33.5 degrees, because the reference angle there is 33.5 degrees. So I'm going to say or 180 minus 33.5 degrees, which is 146.5. But notice 146.5 plus 52 degrees, that's too big. So this is the only one that we actually care about. That's the only one that works. So far, if I go back to these, we're in this first case where we have one triangle because that second angle wasn't going to work. It would add up 146.5 plus 52. That's bigger than 180. I should put all my degrees on here. And we know that all the angles have to add up to 180. So 33.5 is what we've got for our angle B. Let me get rid of all that stuff, and I'll just say B is equal to 33.5 degrees. Well, that's approximate, but whatever. Now we've got two angles, and so we can get the third one. So I know right off the bat that C is going to be 180 degrees minus 52 degrees minus 33.5 degrees. Should I try this in my head? 180 minus 52 is 128 minus 33.5. Oh, never mind. I'm already getting lost. 180. My mental arithmetic is so bad. So I'm typing this into a calculator. I've got 94.5 degrees. That's what I thought. No, I'm just kidding. I didn't know. So there's our third angle. Notice once you've got two, you've got three. And now it should be real easy to find our side length C. Again, I'm going to compare that to these two because I know what these values are. This is an approximation. And so this angle here, angle C, is also an approximation. But I want to not use this angle approximation as well. Now you could think in this case, really, it's the same approximation because whatever we approximated for this angle is going to give us this one, but whatever. I just make it a habit to try and always compare to the given stuff if I can. So I want to find lowercase c. So C, maybe I'll say C over sine of 94.5 degrees is equal, let me get rid of this, is equal to 10 over sine of 52 degrees. And so I've got my lowercase c is equal to 10 sine of 94.5 over sine of 52. And let's go ahead and figure out what that is. 10 times sine of 94.5 divided by sine of 52 degrees is 12.65. Where's my cursor? There we go. So we've got our side length C, angle B, angle C, and that fills out the rest of what we needed. Cool. So there's our one option for our triangle. Here's another case that we've got. We've got a triangle, we've got an angle, and an opposite side length, and so we'll be able to just go from there. So let's see if we can find angle B because we have this side length B. So this is going to be set up in the exact same way. So go ahead, take a look at this. Well, it's gone already, but you hopefully have written down the way that we found this 33.5 degrees and the 146.5 degrees stuff. See if you can figure out what's going on with this one. Give the video a pause if you need it. All right, let me give this a shot. So hopefully you've got something like sine of B equals 20 sine of 50 degrees over 10. So really we're looking at 2 times sine 50. And that is 1.5, 3, blah, blah, blah. And hopefully there's a red flag going up, because this can't happen. Sine B has to equal some value in between -1 and 1. Maybe I'll say since the range of the sine function is -1 to 1. So what does this mean? What this means is that there's no triangle where this is possible. So this is weird because this is just an option. So if we go back to those cases that we had, this is our picture. This opposite side length is too short. If we go back and notice, we notice that B, that was our diagonal side length, is twice the length of A, and A's angle was 50 degrees, which is not terribly small. So this side length right here is too short. Or you could say this angle's too big or whatever, but that's not going to work. So this is actually a pretty easy example once you notice it. People can get really stuck on things and get frustrated with this, but once you see this value, 1.53, whatever, since it's bigger than 1, you know that you can just stop. All right, so if this was, first one was an example of that one triangle situation, and this is an example of no triangle, you can kind of imagine what's going to happen here. So different angle, different side lengths. See if you can find out what angle B is. And really, I'll give you the hint and say what both of the possibilities of angle B are. Go. Pause the video if you haven't. All right, if you're back, let's do this. So we got sine of B is equal to 8 sine of 35 degrees over 6. And again, I'm doing this because I really had sine of B over 8, and then I just multiplied both sides. So this is really, I should have done this already while you were paused. Oh, well. 8 sine 35 over 6 is 0.76. So this leads me to B is sine inverse of all that stuff. I'm leaving a lot unwritten here to save space. And I've got 49.89. Maybe I'll just say 49.9 degrees. Now again, that is right here. And then there's another one right here. And this angle is 180 minus 49.9. And that is 130.1. And notice that if we look at 130.1 and we add that to this angle, there's still room for a third angle. We've got 165.1. That third angle is pretty small, 14.9, but it's there. So this is where we get a little bit weird. We've got two triangles. So what I'm going to do is I'm going to split this up into two cases. I'm going to say on one of them, B is equal to 49.9 degrees. And on the other, B is equal to 130.1 degrees. So what we're going to do is just erase everything. And we're going to solve out the rest of one triangle. I'll do it in blue. And then we'll solve out the rest of the other triangle. We'll do that in red. So from here, things work out really nicely. I know the third angle. I'll do the blue one first. I know C is 180 degrees minus 35 degrees minus 49.9 degrees. Let me grab a calculator because I don't trust my mental math today. 180 minus 35 minus 49.9. That's 95.1. And so now you can find lowercase side length C. And I'll let you do that in a sec. Over here, let's see what our angle is. C, I think I already did this, but it was 180 degrees minus 35 degrees minus 130.1 degrees. That's, what is that? 14.9? Is that right? That's negative 165.1. Yeah, 14.9 degrees. All right, and now you can find a second lowercase c for the side length. So I'll give you a second here to finish this up. I'm just going to divide this right in half because, again, we've got these two options, angle B, angle C, side length C over here, and a different angle B, angle C, side length C. So pause the video, see if you can find those two corresponding side lengths. All right, let's do it. So I've got that B. Oops, I've got my straight line still. There we go. B is going to be sine of 49.9 degrees times 6. I'm using this side length and this angle over sine of 35 degrees. And so that is 6 sine 49.9 over sine of 35 is 7.9-ish. And over here, if I do the same thing, we're going to have, we're going to have 6 times sine of, what am I looking at here? Did I do something wrong? No, I'm okay. Oh, shoot. Yeah, never mind. I did something wrong. My bad. I'm looking at not this one here. Sorry, I'm looking for lowercase c. You guys are probably sitting there going like, what is this idiot doing? And that's okay. Let me go ahead and redo this. Sorry. So lowercase c is going to be 6 times sine of 95.1 over, where's my other angle? It's this one, sine of 35 degrees. So there's my lowercase a, sine of capital A. This is sine of capital C. Perfect. All right, let me do that again. I was wondering why my side length was so close to 8, because that's how I was solving for little lowercase b. So I've got 6 times sine of 95.1 divided by sine of 35. Oops, I typed that in wrong. I forgot the last digit. Oh boy, here we go. All right, over sine of 35. There we go. C, that makes more sense. 10.4-ish. And over here, we're going to get a pretty small value for C. We're going to have 6 times sine of 14.9 degrees over sine of 35 degrees. 6 times sine of 14.9 divided by sine of 35. We've got 2.7-ish. So there's some differences here in the pictures. I'll draw a picture for this. We've got this side length here and an angle. And this angle is 35 degrees. Let me write that in. So that's my angle A. And I'm going to call this side length here B. So that means that angle B is over here. So this angle here is C, 95.1, a bit bigger than a right angle. So it ends up looking like that. And then this side length here, get rid of that. So this is 8. This one here is 6. And this one here, then, is 10.4. And we've got 95.1 degrees. And we've got our other angle, which was 49.9 degrees. So this isn't perfectly to scale. This angle probably should be a bit smaller. This one will end up being a bit bigger then because of that. But our other triangle over here is going to be pretty different. We're still going to have this same setup on our bottom left. So we're going to have some edge here with a 35 degree. That's probably better for that. We're going to still have this 35 degrees here. We're going to still have a side length of 8. But now this angle C is really small. So it's actually coming back through this way. And that means this angle is big, 130.1 degrees, 14.9 degrees. And then we can fill in the side lengths. This side length here is 6, and then you can see this one is real small. It's 2.7. So even though this isn't a perfect drawing, it does look relatively accurate in terms of what's going on. The only difference is that this side length cut through. I should put my straight edge on. This side length cut through this way. Something like that. So that's what this looks like. Hopefully then, what you're going to be able to take away from this is that as long as you kind of keep your wits about you, this shouldn't be too bad. Always keep in mind that there are two possibilities. Sometimes, like in this first example, you'll find that really there aren't two possibilities, because when we found the other one, this other angle was too big. Remember, we found that 146.5 degrees. If we added that to our already existing angle, we do not have a triangle anymore, because our angles add up to more than 180 degrees without a third angle. So keep in mind that there are two possibilities. Just double check the second one. Make sure that it doesn't work or it does. You might find that neither of the possibilities work because your sine of an angle is just going to be too large. 1.5 is outside of the range of the sine function. And if there are two possibilities, just track those down. So I'll always give you the option of saying, hey, if there's a second triangle, let me know what those values are as well. If there's only one, that's okay. If there's none, just let me know. So that's how the law of sine works. It's not too bad in practice. You can use it to solve a whole bunch of different applications, because now you could go back and think about all the applications we used right angles for, right angle trig, and now we just don't need right angle stuff. We can go ahead and use the law of sines. So that works out really nicely. Good luck with this. Jump into the homework, jump into the text. Let me know if you got any questions.